There we go. We are ready.
Okay, yeah, I guess I'll start here. All right, thanks everyone for joining in person and online. We have a very special presenter today, Melinda Webster from the University of Washington. I've known Melinda since she was a toddler. That's not exactly true, but I've known her since very early in her career, I think even when you were a grad student, and has done tremendous stuff since as long as I've known her, even very early in her career. She received her PhD in oceanography with a focus on Arctic sea ice from the University of Washington in 2017. And I believe that's when you had your snow on sea ice paper, right? The original, yeah. And so she did one of the, I would say, seminal papers on snow on sea ice, updated and really improved the assessment of snow on sea ice, which is a major, I think a major research result. And then had the privilege of working with her at NASA Goddard for a little bit as a civil servant. And then she left Goddard not too long after I did, or right? Yeah. And went to the University of Alaska Fairbanks for a couple years, 2 or 3 years. Yeah. And then is now back at the University of Washington, where it all started.
Yeah, made a full circle.
So yeah, she's done over 12 plus polar expeditions, including Mosaic, which people may be familiar with. And so, you know, you've done work spanning satellite, remote sensing, field work, etc. So yeah, great to have you here, and great to hear what you're going to be talking about, which is the snow and the changing Arctic system.
Thank you all. That was a very kind introduction. Thank you so much. And thanks for the opportunity to share this work. My goal is to hopefully show you why snow is a really fun topic to study, and also to hopefully get some of your suggestions on where to go next with some of this work. Can you hear me okay in the room? I kind of have a soft voice. Okay. Just tell me to speak up if it's not loud enough. Okay, so before I begin, I'm showing a conglomeration of a lot of studies, and I have 2 big acknowledgements. One is all the co-authors and colleagues who have helped with the results I'll share today, and also to NSIDC for the awesome data sets that you provide, especially the user guides that come with that to know how to use the data appropriately. Okay, so to kick things off, I think a lot of you know that one of the superpowers of Arctic sea ice is its high albedo. And it's really interesting when you think about this, because sea ice is a very complex medium. It's quite heterogeneous. So depending on where you are in the Arctic and what time of the year that you're there, you can get a very low albedo, something as low as 0.1, or even a really high albedo, close to 0.9. But if you step back and think about, well, what sort of surface conditions cover the Arctic Ocean the most, or to cover the Arctic sea ice the most, the winner is snow. And it doesn't matter if, and also snow happens to be the most reflective surface condition on Arctic sea ice. And it doesn't really matter if the snow is thick, or if it's thin, if it's melting, or if it's cold and dry. And it clearly has some of the most reflective surface properties, given all the ice conditions that you can encounter in the Arctic. And in particular for the summer melt season, it's really about what's happening with thick melting snow, thin cold snow, and melting sea ice. Those are the most reflective surface types on the Arctic sea ice. Now you would think, given how reflective it is, it's providing a shield to the sea ice surface, preventing solar radiation from touching or hitting that sea ice surface and melting it. So it's a good thing for sea ice in terms of mass balance, right? But snow is also quite insulating, and maybe this is not such a good thing for sea ice. I really like the example that Gary Leakett put together in a study from 1978. And so what you're seeing on the right here is thermal conductance as a function of snow depth on the y-axis and sea ice thickness on the x-axis. And the takeaway is that a little bit of snow goes a very long way in reducing the amount of heat flux that can go from the ocean through the ice and snow to the atmosphere. So especially for thin sea ice, Looking at the 0.1 to 0.2 meter sea ice, just a little bit of snow has a pretty big impact on the thermal conductance. And this is really important when you think about the autumn freeze-up season. There's a lot of thin ice, especially these days, so maybe snow is having an increasingly important role for sea ice mass balance. Now, to really drive this point home, I wanted to share some results from Reykjavik. This is the northernmost point in the US in Alaska. And these measurements are from this place called Elson Lagoon, which is right here. It's protected by this land, so the ice isn't dynamic, like hardly at all. It's really a great place if you want to understand sea ice thermodynamics, because the ice doesn't move by the winds or the ocean forcing. So in that way, you can understand in a really nice, or in a very clear way, what the relationship between snow and sea ice is. So what I'm showing in the bottom is a survey that we took of snow depth and ice thickness. So the snow depth is in blue, and the orange or kind of golden color is ice thickness, and they're inversely related. So the thinner the snow cover, the thicker the ice, and vice versa. If you have thick snow, you have thinner ice. What's really cool about this place in Elson Lagoon is once you have snowfall and snow dunes develop on its surface, they tend to stay pretty static, like they stay fixed in place because you have a dominant wind direction. So the snow that accumulated there and the dunes that developed in the autumn are staying there throughout the sea ice growth season, and that's why you get this strong relationship between the snow depth distribution and the ice thickness distribution. So again, thinking about the large scale, zooming out of what's happening in the Arctic, I kind of wonder, with ice thinning in the Arctic, will snow play an increasingly important role in sea ice mass balance and mass budget? So I really like the question that Rob Masson and Matthew Sturm posed for a book chapter in Sea Ice, and the chapter was labeled or titled Snow, Friend or Foe, in relation to sea ice. And I wanted to put forth some ideas of where, or in instances where it can be a friend to sea ice and instances where it can be a foe to sea ice. And thinking about that from the case of thin snow. So this is a really nice study led by Ian Raphael. This is from Mosaic. And so Mosaic began in October 2019, and the flow that they selected was kind of like a skeleton of a flow. It barely survived the summer melt season. It had a lot of open water area around it, and it had remnants of ice that survived. And then the ice evolution process in the winter pursued, and so you had ice growth and a snow cover, and it probably looked more like this by the springtime. But what's really interesting about this is that the snow cover was unusually thin on Mosaic. And Ian had a really nice experiment where he had all these stakes set out in all types of sea ice, the young ice and the old ice. And these stakes were used to measure the sea ice growth and the sea ice melt. And what he found was in the red here, this younger ice, because it had relatively thinner snow than the older ice, it was able to grow faster and catch up to the thickness of the older ice. So maybe in a way, if there's thinner snow on sea ice, it's not such a bad thing because it helps the ice rebound and get thick. But that's not always a good thing to have thin snow. And I wanted to show this case for 2011 in the Beaufort and Chukchi Sea. So this was a really interesting study. I didn't expect to find this, but what I'm showing here in the middle, this is a bird's eye view of a multi-year ice flow. And we generally thought that if it's old ice, it has really thick snow. It's had a lot of time to accumulate snowfall, right? But I don't know if you can see quite clearly, this is pretty wind scoured and it's snow free. And so I've played around with the contrast and you can see it a bit better here. There's a lot of thin snow and snow-free patches on this old ice. That's what we're showing here is the distribution of the snow depth measurements across this multi-year flow. This is a 9-kilometer survey, so it's a pretty statistical, like very good representation of what the snow conditions were like. And you know, less than, or about 50% of the snow was less than 10 centimeters thick. And more importantly, about 40% was less than 5 centimeters thick. So when you get thinner and thinner snow, it's becoming optically thin. You're starting to see the darker surface underneath, which is really important when it comes to sunlight and where those photons get absorbed. Now, in comparison, we looked at the snow on the surrounding first-year ice floes, so the younger ice, and it was unusually thick, both for the underformed first-year ice and the deformed first-year ice. Oh yeah, question.
What's underformed?
Oh yeah, underformed. So can you see these ridges here? This is a
Yeah.
really rough-looking sea ice. So when I say deformed, I'm talking about really roughened ice that's been created through ice motion, convergence of ice flows that can form like miniature mountains. You can also get divergence and have cracks in the ice form. So it's the variability of the surface elevations of the ice. And if it's underformed, it's smooth. It hasn't had as many opportunities to get deformed and to roughen up its surface.
Thank you.
Yeah, feel free to interrupt with more questions too. I don't need a ramble the whole time. Okay. So thinking about this thin snow case, we wondered, well, does this have an impact on the rate of melt, especially surface melt where you have solar absorption, where there's thin snow versus thick snow? It turns out there is a big difference. So what I'm showing here is a ponded ice fraction. And so a melt pond is just a puddle of meltwater that forms on the sea ice surface. They're really beautiful, but the downside is they're much darker than the sea ice. So they absorb more sunlight and melt the ice much faster. And when we compared that multi-year ice area that had the thinner snow with the first year ice area that had thicker snow, there was a very big difference in the timing of when those melt puddles formed. So they formed much earlier in the multi-year sea ice, as much as 3 weeks, which is actually a significant result because this is during the peak insulation period of the summertime. And that's probably the worst time to have a melt pond if you want to survive the melt season. So this is really interesting in thinking about, well, is thin snow good or bad? Really depends on where you are and when you are in the Arctic. So thinking about this a bit more, it would be helpful to know when and where and how much snow there is, and especially what drives the distribution of snow and the timing of snow. And that's what we've been digging into, we being all those co-authors that I listed. We've been looking at this in a variety of ways, and that's what I'd like to show next. So if you needed a cheat sheet to understand where snow in the Arctic is, I think one of the first things that you could look at is the sea ice age, because there's a really strong relationship with the age of the ice and where the thickest snow is. And what you're seeing here on the left, the background snow depth, this is from a spring period, so about March, April. This is nearly the maximum snow depth. And this is from a model result in the background. But these lines, these are retrievals of snow depth from Operation Ice Bridge. The triangles and the stars are all these random in situ data sets that we've just been compiling together to see if it's, vaguely telling us anything about the distribution of snow. And if you kind of squint and blur your eyes, it kind of matches the age of sea ice, right? And that's because ice is a platform that accumulates snow. And if it's had longer time to accumulate that first snowfall of the early autumn season snowfall, you tend to have thicker snow. But this isn't always the case. There are regional differences, and I wanted to highlight this Barents Sea and Kara Sea region where you have lots of seasonal ice there, but you have very, very deep snow. So what's going on with that? Well, we've been looking at this in a number of ways, and I think the examples shown here on the upper plots, this is a really nice picture, snapshot of how the snow accumulation season differs between this North Atlantic region and the Beaufort and Chukchi Sea region. So these buoys have downward facing rangefinders. They're kind of like pingers that you can get at Home Depot or whatever. And what they do is they measure the distance between the surface and the pinger itself. But if you know when the buoy was deployed, what that initial snow depth was, or if it was snow free, you can monitor the snow accumulation and the snow and sea ice melt over time. What we're showing here in this Beaufort Sea example is there's a lot of snow accumulation early on in the autumn, and then it's just kind of boring after that. But in the North Atlantic area, there's a lot of snowfall. It's frequent heavy snowfall events. And this is happening throughout the winter period, even though this cuts off at the end of December. So there's these really distinct differences in the atmospheric forcing that establishes the snow on sea ice in those regions. And that's why there's deeper snow in these regions with seasonal ice. You have a lot more cyclone events, storm events. This is right underneath the North Atlantic storm track. And in this result on the far right, I'll take a moment to explain this because it's a little confusing, but really interesting at the same time, is we wanted to know at what point do cyclones contribute snowfall to establishing the snowpack. So 75% of the peak snow accumulation at that point, these shading, the dark blue, is representing what contribution cyclones have contributed to establishing that snowpack. So for example, in this region, it's about 75% of the cyclone from snowfall goes towards getting that deep snowpack there. In contrast to the Beaufort Sea and East Laptev Sea, you have a much smaller contribution of cyclones. That isn't to say that they're not important. It's just a different type of synoptic event that establishes snow on sea ice in those regions.
Well, then, Melinda, is it a modeling?
It is a modeling result, yeah. So this is based on Era 5, and it's using a Lagrangian ice motion vectors to accumulate snow over time and converting the snowfall to snow depth using the density climatology from North Pole drifting ice stations.
Oh, wow. Okay.
Yeah. I know, we get desperate when we want to know the answers. We'll pull everything into the analysis. Yeah. Any other questions?
So is that Julianne's?
No, this is Ron Kwok's stuff from.
It's Ron Kwok.
Yeah, Ron and Glenn Cunningham, like their 2008 approach for doing
Oh,
this.
okay. Yeah.
So we just swapped it out with Era 5 and then computed that
Yeah,
as well.
cool.
Yeah, I mean, it'd be cool to know what the in situ observations say, but they don't exist.
Yeah, oh, yeah, definitely.
Yeah, so we rely on modeling and now more recently on remote sensing retrievals now that we have ISAT2 and Cryosphere. Okay, so the big takeaway of this result is snow is really governed by two key mechanisms. That's when the timing of sea ice formation, when that happens in the autumn, and also the snowfall patterns, the large scale patterns of precipitation. There's a lot more things happening, as you can see in the schematic. You know, there's wind distribution, there's snow lost into open leads, there's snow ice formation. But I'm just gonna step back and say that the big things for the Central Arctic are ice formation date and precipitation. But as you know, there's been a lot of changes with those two types of relationships because the state of Arctic sea ice has been changing. We have much less multi-year sea ice. We have less ice coverage. So there's kind of two competing ideas of how this might affect snow on Arctic sea ice. One is if we have less ice, we simply have fewer platforms to capture that falling snow. On the other hand, if you have more open ocean, you have a bigger heat and moisture source to facilitate snowfall. So we're not really sure which one's going to win, or maybe there's no change because they have competing or compensating effects rather. So a big question that I have that's been kind of guiding this work a bit is, well, how is snow on sea ice responding to climate change? I think to understand that better than we do now, it's helpful also to know how does snow on sea ice respond to natural climate variability, because they both work together in opposite ways. Okay, so for the long-term changes that we know of for snow on Arctic sea ice is that this Western Arctic sector, especially the Beaufort and Chukchi Sea, there's been a general thinning of snow on sea ice, especially the springtime measurements. And this is a combination of different observational data. So the North Pole drifting ice stations from 1954 to 1991, that's really what's given us the snapshot of the climatology of snow on sea ice. And then we've added to this the Operation Ice Bridge retrievals, ice mass balance buoy retrievals, and I've been trying to extend this to the contemporary period. And what we found is that the trend is more like a 1.5 centimeter per decade decrease from what we saw in this paper. But yeah, the big picture is that we're seeing this decline in the snow cover on Arctic sea ice in this Western Arctic. Now the question is, what's causing this? Is it the precipitation? Is it the sea ice? Or is it both? Now, I want to bring your attention to this panel. This is the snow accumulation rate over time, or you can also look at the, this is a cumulative snow accumulation over time. this is the accumulation rate over time for September, October, and so on. But looking at this one, by the end of the accumulation season, they're all pretty similar. So there's not really a confident thing that we can say that there's been a change in snow accumulation on Arctic sea ice in this western Arctic region. They're very, very similar. So that's not the culprit for thinning the snow on Arctic sea ice. But if we look at the timing of when ice is forming, and this is a really nice figure from Jeff Miller at Goddard, this freeze onset, so these are days of year, is happening later and later and later, by as many as like 3 to 4 weeks. And if this is happening and missing this peak snowfall period, you're going to have less snow overall. And when we try to map this out, this is looking at the timing of sea ice formation on the left here. So again, days of year, and the snow depth distribution, both from an updated climatology from IceBridge and from ice mass balance buoys and field observations. We've seen a thinning in this Beaufort and Chukchi Sea region, and that aligns with this loss of multi-year sea ice and late sea ice formation in this region. So the culprit is really about how the ice state has changed and how that's impacted the snow. So what's happening in the Eastern Arctic? You know, this is all grayed out and we really don't know. We don't have the observations, unfortunately. We're starting to with satellite retrievals, but we don't have that nice time series that we do for the Central and Western Arctic. But we do have some clues of what's going on, and that's thinking about what's happening in the atmosphere, where it's becoming warmer and wetter. And we're seeing a lot more rainy days in the Arctic, especially in the autumn season. So I would say stay tuned. I think there's some really cool model experiments that could be done to better understand the changes in this region, but it's certainly having a different response than what we see in the Beaufort and Chukchi Sea. Okay. Now, I've been talking about the large scale trends in snow on sea ice, but let's talk about the variability. This has been something that's been more complex and difficult to understand, but also a lot more fun in many ways. I want to bring your attention to this trend again, but look at the scatter along that trend line. Like, that's huge. And part of that is due to just being in a different location in the Arctic and sampling what the snow conditions are there. But also part of it is due to just year-to-year variability in the snow conditions. And to give you an idea of just how variable it can be, I like this station number 22 from 1978 to 1982. So in 1 year, they had an average spring snow depth of 38 centimeters. The next year, they had an average snow depth of 80 centimeters. And these are averages over 1,000-kilometer survey lines, so they're pretty robust. That's a big difference, and I've been wondering, well, what causes that difference? And gosh, can we even believe this trend at all, given that huge variability? So we wanted to dig a little bit more to understand, well, what causes the variability in snow on sea ice? And can that better inform how we interpret trends in snow on sea ice? Now, for variability, I was thinking, well, where should I begin with this? This is a really broad question. So I try to narrow it down to thinking about it in 2 ways. Sorry, these are questions that I just said. I wanted to think about it in a more constrained manner. So I wanted to think about it for the summertime, when a little bit of snow goes a very long way in terms of changing the surface albedo. And to give you some context for this, you just need about 0.5 centimeter of cold, dry snow to reflect nearly 80% of the sunlight that hits the surface. Or if it's really coarse grained snow, you need about 2 centimeters. So I was curious, can we see these ephemeral snowfall events have an impact on the albedo? And is that variability tied to what's happening with trends in snow on sea ice? So what could cause snowy summers, or variability in how much snow is present in the summertime? Well, there are kind of 2 easy ideas that probably you've thought of already. That is, well, what's the leftover snow from the winter accumulation? Is it just lingering around? Or are you actually having active new snow accumulation? Is it an atmospheric driven process? So we've started looking into the literature for this. By the literature, I mean, we dug into the diaries of some of the participants from the North Pole drifting ice stations. And it was really cool because, so this is Ivan Happening, I'm probably saying his name wrong. He was on the first drifting ice station in 1937 to 1938, and they really loved having snowy summers. They really did not like melt ponds. So it was really cool to see how much information you could get by just reading about the angst of melt ponds versus, oh, it's a good day, it snowed. And so we know for certain that there's been snowy summers in the past based on these diaries. And we've also started looking at more recent data, like for example, in Mosaic, we found that about 15% of the snow lingered around, but that was mainly beside ridges like this, so it didn't fully melt, but still, there's snow. And then I had a student who did a really nice job in counting how many snowfall events occurred in this ice mass balance buoy record, which is about 180 buoys. She was counting every single one, and she did this in a way of looking at how many events occurred from initially snow-free conditions to new snowfall. And so she found on average from 2000 to 2020 that there's about 2 to 3 snowfall events in the summertime from initially snow-free conditions again. And it's a very thin snow accumulation amount. It's only 2 centimeters, but again, that makes a big difference albedo-wise. She also found that it didn't really last long. There were some events that lasted for like weeks, but in general, they were short-lived. But it was enough to have an effect on the top of the atmosphere radiative forcing. Because of the shift in the albedo, she found it was close to about a 0.1 increase in surface albedo. That resulted in a decrease in the top of the atmosphere radiative forcing of 0.09. So I thought that was pretty cool, but I really love to know if climate models see the same result or show that maybe it doesn't matter, or maybe it's more important. So that's some of the work I've been doing while I've been visiting Boulder this month. Okay, so thinking about this variability, we know that the summers can be snowy. Now we want to know, well, what causes that? Is it natural climate variability? And the first idea that comes to mind is the Arctic Oscillation. So I gotta admit a caveat here. I'm not an atmospheric scientist, but I do think that the snow on the sea ice, I'm pretty sure, is from snowflakes that form in the atmosphere. And precipitation patterns are strongly affected by the Arctic Oscillation, especially when it's a positive phase of the Arctic Oscillation. You have a stronger jet stream, and that allows a lot more cyclones to go into the Arctic. And from the previous results, I showed that was an important mechanism for the winter time snow on sea ice. We wanted to know if that was an important mechanism for the summertime snow on sea ice. So that's what we wanted to look into next. And we're using a whole bunch of different data sets to look at this, but the primary one is the snow model LG. This is developed by Glenn Liston and others. The data set's hosted at NSIBC. We're really interested in this product because it actually simulates melt. There aren't a lot of snow models in sea ice that actually have that parameterization. There are sea ice models that do it like SICE, but this is a standalone process, snow process model. So it's really easy to use and interpret. So what it does is it accumulates snow along these Lagrangian ice motion vectors here. So this is just resampling to show you a general idea of what that looks like. And if you want to know the nuts and bolts of it, you can ask Mark because he developed it. And thinking about what it looks like for the summertime is that, yeah, there's snow on sea ice based on this model. It's showing that it definitely exists for June, July, August. So this is a good product to work with for us. We also threw a lot of other products at this analysis. So albedo, melt and freeze onset dates, ice concentration, and so forth. Now, the snow model LG, this has been pretty well validated for the wintertime and spring season, and it looks pretty good, but I hadn't seen anything about the summertime, so we looked at that a little bit to know what we were getting ourselves into, especially in terms of biases. So on the left, I'm showing the snow depth per month, and this is from the North Pole drifting ice stations in dark blue and ice mass balance buoys in yellow. So these are 2 different types of measurements. And also there are 2 very distinct periods from being sampled on Arctic sea ice. But the big takeaway is that there's generally some snow that's present during the summertime. And the model, like we're looking at different regions here, shows that the snow melts away entirely. So the big caveat here is the model does show snow on sea ice in the summertime, and it actually shows more frequent snowfall, but it's very little amounts compared to the observations. And because there's less accumulation, it melts faster. It also melts too quickly when it gets the accumulated amount, correct? So perhaps the model is being forced by something that's a little too warm. So that's the caveat when we see these next results, is that the model melts snow too quickly, but it's still pretty good. We're happy with it. Okay. Now, where do we begin with our science questions? Because that was a very broad question I asked before, is, well, what drives the variability of snow on sea ice? So thinking about how to approach this, there's that one idea of maybe it's leftover snow, or maybe we could call it preconditioning. So there could be a relationship in the timing of ice formation, allowing a lot of snow to accumulate during the wintertime, and then maybe it just lingers in the spring and summer melt season. Or maybe it's just snowing a lot, that has a strong dependency on the air temperature, both aloft and at the surface. So if you have new snowfall and maybe it's colder, it can last for a long time. And then I guess it's important to ask this, does it even matter? Is it important? And how do we define what's important? For that, we looked at the surface albedo. If it made a measurable effect on the surface albedo, then we would say, yeah, it seems important. Let's do more research in the future. So to begin, I first want to walk through what we found in terms of the Arctic Oscillation and snow on sea ice. And what we found is that there is a really strong relationship with that. I still haven't quite figured out how to show these results in a clean way because there's about 40 maps. So I'm just showing June, July, August averages rather than monthly results. And I'm just showing what was significant as a result. So if you want more details, I'm happy to chat. So what we found is both the correlation between the snow depth anomalies and the Arctic Oscillation were very positive. And when you regress the snow depth anomalies onto the AO, that's also a strong relationship. The linear response was strong, and the first principle component showed the spatial pattern of when you have a positive AO, you tend to have more snow on Arctic sea ice. And so to give you some context, the model suggests that there is about 4 to 5 centimeters more snow in the central Arctic during these positive AO summers, which should be a significant impact on the surface albedo. So that's what we looked at next from the satellite project. And this is a little tricky to do because in the summertime, you have different ice concentrations. So what we did is we looked in the central Arctic where ice is continuously above 80% ice concentration to see if there was an albedo impact, and we saw that it increased by 0.1. So that was a really cool result saying that, hey, it's snowier and it has an albedo impact, but that doesn't really address the question of, hey, was that leftover snow or new snow? So that's what we started to dig into next. Now this is looking at the question of, is this leftover snow? And I just want to bring your attention to this bottom panel for the sake of time. We looked at a lagged analysis of monthly snow depth anomalies, and we found that the spring snow depth is really quite strongly related to what's happening in snow depth variability in June. That's huge because that's when you have the most photons hitting the surface. So if you have an idea of what was measured in the springtime, which happens to be a time where remote sensing retrievals are most reliable, that can give you a really good indication of what the surface melt rate is like in June. But from July onward, that relationship breaks down. So it really doesn't matter what happened in the spring. July and August are a totally different story. So what's happening there? That's what we looked at from that atmospheric perspective. And so again, I spliced a lot of results here, and I'll try to walk through them slowly. If you have questions, please ask. And that's also why there's like 4 panel Bs here. But okay, for a positive AO summer, we looked at these both on a monthly time scale and averaged across June, July, August. But what we found for a positive AO summer, there are a lot more cyclones in the Arctic. So this is the correlation between the cyclone count and the AO, and they're penetrating deeper into the central Arctic, and they're also stronger. You can ignore the yellow dots. They don't mean anything in this context, but they're also stronger. So you need one more ingredient to have snowfall with strong cyclones, and you need cooler temperatures aloft. So this really helps facilitate a lot more precipitation, but precipitation coming in the form of snow. I thought that was a really cool result because it's suggesting that in July and August, you have more frequent snowfall, and that's what's causing these snowy summers during those months.
And that's what's causing what?
The snowy summers during those months.
Thank
Yeah, of course. So we also looked at the surface air temperature. So maybe it's just colder and the snow can last longer because it's not melting away as quickly. And the relationship was not statistically significant. So we can't say with confidence that, yeah, it's colder, so the snow will last. But there's also a caveat with that because we're using ERA 5 and we know that ERA 5 doesn't explicitly represent snow and sea ice. So maybe it's hard to say with confidence whether or not that's a true result. I tend to think it's probably not significantly cold, but again, it'd be better to look at this using a different reanalysis project. So any questions there? Because that was the hardest slide to walk through. No? Okay. So stepping back, what causes these snowy summers? Well, for the June period, it's all about what happened in the spring. What was that maximum snow depth? But later on, it's about what's happening in the atmosphere. And we found that there's a very strong relationship with what's happening with the Arctic Oscillation Index. But interestingly, oh yeah, and I did increase the albedo. But interestingly, this relationship doesn't hold. It starts breaking down in 2007. So we did an analysis of what the relationship was like before 2007 and after 2007. And nothing was statistically significant after 2007. And this has, I don't think this is due to any changes in the Arctic Oscillation Index. There's no trend in that. Unlike the wintertime, there is a trend. So we really don't know what's going on there. We're guessing it's just so warm in the Arctic now that maybe when snow does accumulate, it doesn't last long, or maybe there's just not as much snowfall. And also maybe there's less sea ice area to capture that falling snow. So
Yeah, I just want to mention that 2007 is stuck in my mind.
Yeah.
Because if you're looking at a animation of sea ice extent fields, it's in 2007 that there's a startling drop. I mean, it's just startling, so.
yeah, it's shocking. And it's like, well, maybe our sample size is just so small now that we can't find a relationship. So one of the things I'm curious about is, can a climate model show this? Like, does it also show a breakdown in this relationship because of ice loss or because of it being so warm? Like, that's one of the questions I have that I hope we can address as CSM too.
Yeah, and you don't, the AO and the sea ice extent, September sea extent starts to break down around that time too.
Oh,
you know?
really? Okay,
Yeah.
for the winter time.
Yeah, so yeah, the wintertime AO and the, you know, that,
Yeah, okay.
the Ignatius and,
Yeah.
like you don't really see that anymore.
It's so interesting. Well, that's a good heads up because I was thinking, well, we should look at this for the wintertime snow. So I'll keep that in mind.
Yeah, I mean, it'd be interesting to see what it does with snow, but the ice cover doesn't seem.
Yeah. Gosh. So those are some of the open-ended questions that we have. And so coming back to this idea, well, what do climate models show? Would they show the same response? And so we've been looking at snow on sea ice with the community air system model. I'm wondering, you know, how will snow respond to climate change in the future? And coming back to these two ideas, you could have less sea ice area, so you have a smaller platform to accumulate snow, or maybe you have more snowfall because you have more open ocean as a moisture source. I wanted to dig into this a little bit with the model results and ask this question of also a very different question. Will the Arctic undergo this Antarctification? I don't know if you all have heard about this, but it's a really interesting idea. So there are projected increases in Arctic snowfall, and there are projected decreases in sea ice thickness. And so if you have thinner ice but thicker snow, you might have a situation where you get more Antarctic dominant processes like snow ice formation. And for those of you who are not familiar with this, a really good way to think of it is you just have so much snow and it's really heavy and depresses the sea ice under sea level. So you get a flooding of seawater in the snowpack. And this is actually what it looks like. This is an example from Steffi Arndt from the Antarctic. And this is a really good example of a dominant Antarctic snow process because the snow on Antarctic sea ice is so much deeper than what we typically get in the Arctic. It's about half. It's pretty crazy. So a way to think of this is snow ice is bad for snow, but it's good for sea ice, because if it's cold enough, then you get a positive mass contribution to the sea ice. So we were wondering, well, how will snow respond to climate change in the future? Will Arctic snow be more like Antarctic snow? What we found is actually the snow cover thins under these different projections. So that's what you're seeing here is the annual mean snow depth. I think I need to read back, but I think this is just for 80 degrees north. But under these different scenarios, the snow thins. And the reason for this is all about timing. So you're seeing here on the bottom left, this is January through December, and these are the snowfall cycles for different decades. And in the 2050s, there's this peak in October. And if you look at the ice concentration in October, there's not a whole lot of sea ice there. And the ice is very thin, but it's because we don't have that platform to capture that falling snow. So even though there's a projected increase in snowfall, we get thinner snow on sea ice in the Arctic. But that doesn't answer the question about this potential Antarctification. Maybe we'll see more snow ice formation in the Arctic. So we looked at the snow mass budget for CSM2. And this is for different decades from the 1950s, 2000s, 2050s. And what's interesting is that you don't get an increase in snow ice formation. And that's because you still have ice that's relatively thick compared to the snowpack. So it's still not enough snow to depress that sea ice surface below sea level to form snow ice. But this is an average from 80 degrees north. I think a really interesting question is to think about, well, what's happening regionally, because there are different dominant snow ice processes in different regions. So I wanted to highlight this, looking at the snow mass gain from snowfall on the top. So this is from spring, summer, autumn, and winter. And this is the snow ice formation for those different seasons. You can see there's some really big differences in like Bering Strait and Fram Strait. And maybe I'm wrong, this is my opinion, but I don't feel like there's enough attention on these more southerly regions. I think they have very distinct snow, atmosphere, ice couplings than what we see in the Central Arctic. So maybe there's something more to be learned from these regions and what could potentially be conditions in a future Central Arctic. Okay, so I'm nearly done, but I want to highlight one more thing. And this is coming back to the question of, is snow a friend or foe to sea ice in a warmer climate? And I wanted to highlight this really nice study by Marika Holland and others. And I thought this was so cool. So what she did is she cranked the snowfall down and cranked the snowfall up to see how the sea ice would respond to more or less snow accumulation. So this top panel is showing the snow volume. So you can think of it as having more or less snow. This pink line is a lot of snow, 1.7 times the amount of normal snowfall in the model. And cranking it down to 0, that dark blue line where there's no snow accumulation. This is for the northern hemisphere, and this is for the southern hemisphere. And the middle panels are showing the ice volume response by month, and then the ice area response by month. And what's really cool about this is these results indicate that snow is a friend. And I love this result because it's a friend for two very different reasons, depending on whether you're in the Arctic or the Antarctic. So for the Arctic, it's all about the albedo effect of snow. If you have more snow, you can have a longer lasting albedo effect that allows snow to survive the summer melt season and grow thicker over time. So the result that you're seeing here in the dark blue, that's a proportion of multi-year ice in the model. Now, in the Antarctic, you have more sea ice because you have more snow ice formation. So for a completely different mechanism, you can enhance the sea ice coverage through more snow. So I thought that was really cool. It's just nice to know that snow's a friend. All right, to wrap up, we talked about a lot of things today, but the one general takeaway is that the large scale snow distribution, if you had to hurry and make a map of it, just think about the age of the sea ice and maybe the snowfall patterns and you'll vaguely get it right. But I think there's also a lot to be learned there in terms of regional differences. Now, we also learned that snow on sea ice in the Western Arctic has thinned, and this is mainly driven by the loss of multi-year sea ice. but we still have a lot to learn for the Eastern Arctic, and I think there's a lot of new opportunities with remote sensing retrievals in that respect. Now, we also looked at the variability in snow, especially during the summertime, and it's really a complicated story. You know, June variance of snow is driven by what happened in the preceding spring. But then from July and August, it's about what's happening in the atmosphere in terms of snowfall amounts. And also this interesting breakdown of that relationship with the AO in 2007, probably due to sea ice loss. And it'd be really cool to learn more with modeling results, what that means. And then what will snow be like in the future? Well, CSM2 suggests that it's going to be thinner and less persistent in the Central Arctic, but it'd be really nice to see what other models suggest. You know, this is just one, and there's going to be CSM3 coming online soon. It'd be really interesting to dig into these same questions to see how they've varied, especially because a lot of the snow physics have been improved in the model. And then lastly, is snow a friend or foe? If you have an answer to that, please let me know. I'm still in. Yeah, maybe it's both.
Friend with an asterisk.
Yeah, and I think maybe snow will always be a friend. All right, with that, I'm happy to take questions. Thank you.
Do you have a question? Yeah.
Maybe in terms of the impact of cyclone to June snow accumulation.
Yeah,
I feel like if the cyclone becomes so strong, then maybe there's a impact of wind, like wind blows up the snow, so maybe redistribute the snow, like loss of snow to water or something like that. So can we just neglect that impact on the summer snow, or is it small?
yeah, I don't think we should neglect that impact. I think you're spot on with that question. Especially in the summertime where it takes longer for leads to refreeze, you would tend to have a greater snow loss into those leads. A lot of these snow accumulation events, and I didn't mention this before, but in Hannah Chapman-Dutton's paper, she looked at the surface air temperature during the snow accumulation events, and it was freezing for quite some time. So I would guess that the leads would freeze over relatively quickly. So that might counteract that snow loss potential. But it's a great question, and I'd love to dig into that a bit more. Yeah, give me something good to think about. Thank you.
Thank you.
Yes, no?
I was just wondering, I'm sure this is in the longer term plans, but to extend your snow accumulation by using ISAT2 onto the record, and then, you know, obviously the first thing to do if you're extending it is to see how well it lines up with what you've got so far. And maybe there's like a big discontinuity there, and so it's like,
Yeah.
that may not be a good extension of a climate record, but
Oh,
maybe you've already looked at that.
I'm really glad you raised that question, because that's exactly what I want to do.
Oh, okay.
I started looking at some of the snow depth retrievals from ISAT2 and Cryosphere produced by
Yeah.
Sarah Cassini, and trying to align those with some of the ice mass balance buoys, which is kind of, it's silly a little bit to compare a 25 kilometer grid product to a point measurement, but
Yeah.
that's literally
I
the
do that
best we
all the
can
time.
do. So it's really
It's tough,
challenging.
yeah.
And there are some snow depth surveys that we can compare with. But yeah, it's really challenging to know like how good it is, given how sparse the field
Right.
measurements are, but that's exactly what I'd like to do, to see what that trend is like. And if we can trust that trend at all with these new capabilities.
Yeah, I don't know if they do this with the snow product, but with the ice product, they do like a 25 kilometer grid average of ice
Yeah.
thickness.
Yeah.
I don't know if they do that with the snow product, and then I'm
Oh,
not sure, because I'm finding out how useful that is going to be here.
yeah, I would
That's
love to.
That's another version of the product, but I'm not sure if they did that with.
Yeah, I'd love to learn more about that, especially if you're thinking of digging into that. I wasn't sure how much of a can of worms it would be to look at the along track retrievals where the ISAT2 and Cryosphere sort of pass over. You have to do some averaging because of the time difference.
Right.
But I kind of wonder if that might be a little more reasonable to compare with, but it'd be a lot more data to work with.
Yeah.
So definitely a great idea, and I'd like to chat more about that. Yes.
Chris Picard has a question.
Hi, Melinda. Can everyone hear me?
Yes.
I had a question about the snow depth persisting through the summer. I think there was a figure on it, but I may have missed the detail. But can you just touch on how much is surviving through the summer and how much of that base snow that we're getting at the start of the growth season in October and November?
Yeah, that's a great question. Thanks for asking that. So it kind of varies from year to year, but I speak to the observational results that we dug into. And for example, for Mosaic, about 15% of the snow survived in those snowdrifts. And they started out at about 120 centimeters in their deepest amount. And the drifts were about 3 to 4 meters laterally. And by the end of July, it was more like 20 centimeters depth. And the snow wasn't that fluffy white stuff that you tend to think of for the springtime. It was extremely coarse grained. Like some of the grains were about a centimeter wide. So that's a case of Mosaic. And for some of the buoy data, those are point measurements, but I would say about 10 to 20% of those showed a persistence of snow that was fairly thin, less than 5 centimeters. But again, those are point measurements, so it's hard to place those in the context of the spatial distribution. Does that help answer your question? Should I try again?
Definitely. No, that's great. Thank you.
Okay, awesome.
A quick question. I really like this idea of comparing the two poles, and I know we're often thinking about a warming world because that's what the world we're in. But what about a cooling world where the sea ice starts to expand into the storm tracks in the northern hemisphere? Do you think that there's potential for snow ice formation in that type of environment? Because it seems like it may be a little bit more like the Antarctic regime that we're seeing.
Totally. Yeah, I absolutely think so. And I think we don't have to wait for the sea ice to expand to get those conditions. Like, again, limited by observations, but my gut feeling tells me that I think that's what's already happening in Bering Strait, and not uncommonly in Fram Strait, given how large the heat flux there is, ocean heat flux there is from the North Atlantic waters. There's been evidence of snow ice formation there from measurements by Don Perovich and forget his first name, Tucker, from the 1980s.
Terry Tucker.
Yes, thank you. And they took ice cores that showed snow ice in them. So I think there already are some places where that's happening.
And I think there was the Norwegian, the N-ice
Yes,
experiment.
exactly.
Max Gronsgag and Sebastian
Yeah.
Gerlin were out in the springtime on Svalbard and saw quite a bit of snow ice
Yeah.
formation, if I remember right.
Yeah, absolutely. That's 2015.
Yeah, 2015.
So I think we can already be there to observe it if we just go there often enough.
I wonder if you could just say some general words about using old data with new data. Like you rely a lot on the North Pole drifting station data, and also underneath or drawing from that, I guess, is Steve Warren's climatology,
Yeah.
you know, which he somehow managed to come up with a climatology of snow depth based on, I think, the North Pole drifting station
Right.
data pretty much exclusively. But, you know, one question we always ask ourselves is how we have access to a lot of really old data. How useful is it, and how do you use it? How do you make it useful? How do you assess its validity, I guess?
Yeah, that's a wonderful question. So for the North Pole drifting ice station data as an example, and I'm saying this for everyone, I know you already know this, but there are two types of snow data sets for that, and snow depth data sets for that. There's the stake data, so they had stakes where they measured the snow depth over time. They also had the transect data that were 500 meters to 1,000 meters long, taking measurements every 10 meters. And we found that the stake data was biased. And so that's where we've tended to not touch that data as much. And Steve Warren did a really nice analysis of that bias.
Oh, okay. So he was able to determine that it was biased.
Yeah, it was really nice. And I think it had to do with where they were placed near some of the infrastructure. So they had some drift formation. Yeah, they got some really cool summertime results that I wouldn't trust.
Yeah.
And so for that reason, having that context we've tended to use the transect data for the historical measurements, but I've also found that the diaries are really insightful for where they exist, and maybe that's sort of a gray data, like photographs, diaries, field logs. I feel like that's a gold mine of information that's really hard to put out there how valuable it is unless you're getting your hands really dirty with the data.
Yeah, that's good to hear. Thanks for crediting NSIDC's user guides, because we try to throw that sort of thing, as much as we can get into them.
I love them. Yeah, thank you.
Yeah, speaking kind of you mentioned the data you have is 54 to 91, but you also showed like the 1937
Yeah.
when the station started. Is that there just wasn't good data in the 30s or into the 50s until 1954?
So they had the first North Pole drifting ice station didn't take the transect data of snow depth, so that's why we didn't include that. And maybe I think there was another station in 1938, but maybe that data didn't become available.
I don't know about that. I know there was a big gap between the
Yeah.
1930 station and
There was the Russians
There-
were
yeah, there was that.
preoccupied with other things. I
They're
guess.
kind of
Yeah.
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 But in 1954 is where the standardized
Where they-
transect
Yeah, okay.
data came about, and so we try to be consistent in our choice of starting point. But I still learned a ton from the diary for 1937.
Did you have it translated? How did you?
It's available as translated into English on all sorts of like Amazon and Barnes and Noble, but there is a copy in the library at Polar Science Center. Yeah, it's really cool.
Hey, I appreciate that you use a wide range of data and then slice the spatiotemporal components of this in interesting ways. And if you were to design a field experiment or a set of instrumentation to do that, like you're like, okay, we have a bunch of interesting questions about the spatial-temporal scales. What would you design? Like the buoys, say next 30 years, what kind of buoys would you put out? How many of them?
Oh, yeah.
This dream world.
Yeah, I have many dreams, in the context of the 5th International Polar Year coming up, I think there could be a lot of opportunity to have distributed networks of observations. I'm thinking of snow, sorry, snow observations in different regions in the Arctic for the same year, also for the Antarctic for the same year, and trying to pin down some of the processes that are causing them to diverge or to be similar. So understanding the atmospheric forcing, the ocean heat flux, and maybe it's a whole array of different types of buoys, like ice mass balance buoys. There's a really cool snow instrument called snowtatos. Maybe you've heard of this? Yeah, Ian Raphael created this, but it's really cool because it's basically a network of snow depth measurements over kilometers around. So you can get a really good sense of the spatial variability in snow, and these can talk to one another and give you a really nice time series without having to actively go into the field and take measurements, which is really nice when the ice is thinner and less stable than it used to be. So something like that I think would be pretty eye-opening paired with meteorological measurements. I could ramble on a lot more about dreams, but I'll come to people and let them go if they need to.
All right, any last questions? We should probably wrap up here at noon. So. All right.
Thank you so much.
Well, thanks a lot. Thank you.
And thanks online.